All right, we are ready. So today we're going to talk about section 10.3, continuing our unit with circles. We're going to talk about chords today. All right, so again, we'll do a little bit of notes today, and then tomorrow we'll take a notes break. Starting out the morning with bad handwriting. Try that again. All right, so what we're going to look at is how chords are related to central angles and intercepted arcs. Okay. So a chord of a circle is simply a line segment whose endpoints rest on the circumference of the circle. So we could label this chord AB if we wanted to. Okay, a diameter of a circle is a chord of a circle, right? It's one that passes exactly through the center of the circle. But they can really pass through the circle any place. They just wouldn't be defined as a diameter, except for if they pass through the center. And the only rule is that they have to just have endpoints on the circumference. We'll jump right in with the theorem. Okay, so if two chords in a circle or in congruent circles are congruent, then their central angles are congruent. I think. All right, so if I were to sketch out a circle here, and perhaps I have two chords that are congruent. Okay, so they're the same length. I'll call this one MN, and we'll call this one PQ. Okay, so if these chords happen to be congruent, then that means their central angles, is the angles that extend from the center and meet at the endpoints of the chord. I know that these angles will be congruent to each other as well. Okay, I'll call this point T in the middle. And then what we could say is, we could say if MN is congruent to PQ, then angle MTN is congruent to PTQ. Any questions? So the converse of this theorem would simply be if central angles are congruent, then their corresponding chords are congruent. Okay, so just going to write the converse here. Right, so remember if you have a statement, if P then Q, the converse is just the other way around, if Q then P. So we'll say if two, you don't even need to say two, we'll just say if central angles congruent circles are congruent. All right, then that means their chords are congruent. That's the converse of theorem 10.3. All right, and just to give you kind of a little view into what we're doing today, it's a lot of theorems. Okay, so it's just lots of theorems up to theorem 10.7, then a couple of examples. All right, so today is theorem day. Does anybody need more time looking at this one? Another second? All right. Okay, so next we'll take a look at theorem 10.4 and its converse. All right, so this theorem says that if two arcs in a circle or in congruent circles are congruent, then their chords are congruent. So for example, if we have a circle here, right, and just label them MN and PQ again. All right, so maybe we have arc MN right here and arc PQ. Okay, and if these arcs are congruent to each other, then their corresponding chords will also be congruent. Okay, so arc MN, if it's congruent to PQ, then segment MN congruent to segment PQ. right, and then of course the converse is also true. All right, so that would be the converse. Moving through the list, theorem 10.5. Okay, so this one says that if you have chords that are equidistant from the center of a circle or from the centers of congruent circles, then those chords are congruent. So that would look something like this, right? If we have circle here, okay, and then I'll label these chords. These two I'll just call A, B, C, and D. And what happens is if they are equidistant from the circle's center, then we know these chords will be congruent to each other. Okay, so I'm going to let this be point E and point F. So we could say something like this. We could say if SE is congruent to SF, then AB is congruent to DC. Any questions on that one? All right, and then the converse is also true. Okay, so I'll leave that there for just a second. Let's see how we're doing. We've got 2 more theorems. And a couple of examples. Does anyone need more time here? Okay. All good? Okay, fantastic. So moving on to theorem 10.6. All right, so if a diameter is perpendicular to a chord, then it bisects the chord. Right, of course, a diameter itself is also a chord. So here's point P. Let this be the diameter. Okay, and so if I have a chord right here, we'll call this one BA or AB. Okay, so if this forms a perpendicular, then that means it's also acting as a bisector. Okay, so we can say if CD is a diameter and is perpendicular to AB, and that means, I should label a point here. Let's call this E. Okay, then that means AE and BE are congruent. Any questions there? And then of course, just the converse. So the converse would just be if a diameter bisects a chord, then it is perpendicular to it. All right, one more theorem. Okay, and this one just says that the perpendicular bisector of a chord contains the center of the circle. So it's kind of a follow-up to theorem 10.6. So again, we have chord AB. And basically, we're just saying that that perpendicular bisector is going to include the circle center, right? Which we kind of see from the previous theorem as well. Okay. Any questions? Alex? Okay, let's do a couple of examples together. All right, I'll spare you the 9-step proof. We'll just get into some examples.
Wait, there's a 9-step proof.
Not right now. So yeah,
Thank you.
yeah. I mean, it's an okay one, but I don't think it actually will add too much to our. We can do without that particular one. However, we will do a couple of examples. Okay, so we have a little circle here. And I'll let this chord be, I want it to pass through the center. All right, pretend that passes through the center. Okay, and then this one we'll call, this will be CB. All right, so we have angle 1, 2, 3, and 4. This is point Q right here. All right, so if the measure of BD is 100, right, so if we know this is 100 degrees, okay, so we want to find, wait, that can't be right. All right, yeah, I guess it is that easy. All right, so that's too easy, you guys. I'm sorry, this is just too easy. So here's point Q. So actually I should call it like angle DQB, which is also the same as angle 4. And basically that's also 100 degrees. Yeah, that's actually too easy, right? So we learned this in the last section too. The measure of the arc is going to be the same as the measure of the central angle. Yeah, that one is so easy. I'm like, wait a minute. Okay. All right, the next one's a little harder. Okay, so for this next one, we're going to solve for x. So let point O be at the center. X will extend from the center to the circumference, so that means it's a radius. Okay, then I have some chord up here. I'll call it BC. Okay, and then right here, we'll let this be 3.4. Okay, and this little piece is perpendicular to the chord, and the length is 4. All right, so if I want to find the value of X, I know that X is a radius. All right, I also know that this segment right here is bisecting the chord, right? That means that it's breaking it up into 2 congruent parts. So we have 2 here and 2 here. All right, and if this is the radius that we want to find, I also know I can draw another radius right here from the center to point C, and that these will both be congruent, right? The radius will always be the same measure within a circle. So from here, all you have to do is use the Pythagorean theorem, right? So we could say 3.4 squared plus 2 squared equals x squared. All right, and we can work it out. So we have 3.4 squared plus 2 squared, which is 4. That gives us 15.56. Right, so that's x squared. Okay, and then we just take the square root of that. Okay, so then square root 15.56. All right, so we end up with about 3.94. Any questions for that one? So we'll leave things here for the lecture part. I'm going to go ahead and end the screen share and process the recording, put this into my courses later.